Okay, this is one of the toughest problems that we have. First, we're going to make a buffer, and then we're going to add HCl to it. So the first one, we're going to have to combine HF and F minus, like we did before. So we're going to have to change to moles to figure out the new concentrations. And then we're going to add 95 mils of this buffer that we just made to 5 mils of HCl. So we're going to have to change to moles again. Then we're going to have to react the HCl with one or the other of the parts of the buffer. And then once we do that, then we put it back into the equation to find the pH. So the Ka expression, I guess, in this case. So let's do this out. First part is just like what we did in the previous lecture. We have to determine the concentrations after mixing. So this is a little different in the volumes because I was just going to use the concentrations from the previous problem, but I always hated those on the exams. You'd like to have a fresh start each time. So that's what we're going to do here. We're going to just start it all over again. And this comes up to be 0.0248 moles of HF and 0.0113. And I should warn you, we're definitely going to have to go to a second piece of paper. So you might have to backtrack to look at some of these previous calculations as we go along. Now we have in the moles, and we have our new volume, which is 0.1. Now that's a gift. When you do something like that, or I do something like that on the exam, it's to help out, because if you divide by, if you have 55 mils and 45 mils, that's 100 mils, or 0.1 liters. And all that's going to do is shift the decimal place over one to the right. It's a gift because it's very hard to make a mistake on the calculation. You can certainly plug it into your, shouldn't have that minus, shouldn't have, you should be able to just do it without the calculator, but if you have to, that's fine, and even that will be easier than having to put in, like we did, 0.09. So there's less chance of making a mistake, is what I'm getting at. Now, this is not part of the problem, but I do want to show this. If we take HF, so we've made a buffer. Let's find out what its pH is, just so that we can check, because we're going to add an acid to the buffer. And a buffer, what it's supposed to do is prevent the pH from changing very much. So if we put these values in, minus x, plus x, plus x. So though this was not asked for in the problem, I'm doing it out so that we can see what change occurred. Anytime you add an acid to a buffer, the pH is going to drop. It has to. It's not magic. It's not going to hold it absolutely steady, but it shouldn't change as much as it would if you just put acid into an unbuffered system. So this is what do we have here? Let me get this right. Oh, 6.80 times 10 to the, and I'm going to do this. I'll stop here. Solving for x, the concentration, taking the negative log, we'd end up with a pH of 2.82. Since this isn't part of the problem, it's just something that we'll check when we're done. Okay, so the pH of this buffer solution before we add the acid is 2.82. Okay, now what we're going to do, the part that we're asked to do on in the problem is to take 95 mils of the buffer and mix it with 5 mils of the acid. So since we're mixing, we have to change from concentration to moles. So we have 95 mils of the buffer. I'm trying to find here are our concentrations. So these are our new concentrations. So we just multiply them by the volume, which is 0.095. And this is 0.113. So we made our buffer. Now we're taking a sample of it, 95 mils. And we're going to mix it with 5 mils of the acid. Now that's not very much, but it certainly is going to change the volume. So we have to, when we're changing the volume, when we're mixing things together, we have to change to moles. Then we have 0.0005 moles of HCl. Okay, now these are the moles of things that we have in this new solution. We have our weak acid, we have its conjugate base, and we have the HCl. HCl is a strong acid, so it's going to react 100% with one of these two species. Well, it's not going to react with the acid when it has a base that's present, and that's what the buffer is supposed to do. It offers an acid and a base to react with any strong acid or strong base that we put in there. So these two are going to react together. Now what happens during the reaction, we have HCl plus HF, or F minus, I should say. So the acid and the weak base, or the conjugate base of HF. And this, we don't put a return arrow, we don't put a double arrow because it goes 100%. We produce HF, and then Cl minus, which plays no part here in the rest of this calculation. So we'll just do it by moles first before we do anything, before we convert back to concentration. You can certainly convert back to concentration if you want, but I like to leave it in moles before, and then this is 0. Now the HCl, the point of a buffer is to use to neutralize all of the acid or base that's put into it and still remain intact. So this number should be less than this one. If this was larger, then you've destroyed your buffer. So all of this gets used up. So we use up the same amount. It's 1 to 1, so we use up the same amount here. And this side gains it. This is the important thing to remember. A lot of times people will remember, of course they'll remember to get rid of the strong acid. And they'll get rid of this side, but they'll forget to add it to this side. And then we get the same amount of Cl. So this is 0. This is 0.0102 moles. Let me make sure that that's right. And then this side is 0.0241 moles, and then this is 0.0005. And we don't care about this one. It's nice that that happened, but we are looking for these two. So the buffer did its job. It destroyed or neutralized all of that HCl. It's gone now. And by doing that, it reacted some of the F minus, but in the process, it created HF, which is what it's supposed to do. So we used up some of the conjugate base, and we created some of the conjugate acid. So after neutralizing that, or buffering that strong acid, it's still now we're down to the two components again. We've gotten rid of the strong acid. We have F minus and HF in different amounts now. So, but there's still measurable amounts of each, so the buffer is still intact. Now we divide by the new volume. We had 95 mils of the buffer that contained HF and F minus, and we added 5 mils of HCl to it, so we have 0.1. And so this becomes 0.102 molar. F minus, make sure I get that set up correctly, and then 0.241 molar HF. After all of that, now we can finally put it into the expression that we would have liked to work with immediately. We couldn't. We had a lot of setup. So, but we're back to our Ka expression, just like the very first problem that we did. We have ICE, so we have 0.241 molar. This side 0, and this is 0.102 molar. Minus x, plus x, plus x. Very familiar now. So just a lot of setup for these buffer problems to get us back to the original problem that we've done many times. So if you can get through all of that at this point, then it's a piece of cake, because at this point it's getting back to one of the very first problems that we've done in this acid-base chapter. The concentration, this is H3O plus, so there's no need to. The last one we had OH minus. Well, that was in the previous problem, but or previous lecture. But here we have H3O plus, so we can convert directly to pH. And we see that the previous, what was the pH of, it was a pH of 2.82, and it went to 2.7. It should drop, but it shouldn't drop significantly. If we had just put the HCl alone, 0.1 molar HCl has a pH of 1. So this, if we had put HCl directly into water, it would have diluted it by 10 times, so it would have dropped to, a pH of 2. This prevented it from dropping very much at all. So that's what a buffer is supposed to do. So your answer, since we added a strong acid, it should drop from the pH of the buffer alone, but not a tremendous amount. Okay? All right, let's try another one here. Go a little bit faster. So we're going to find the buffer. We'll find the pH of it, even though they don't ask for it, but we're going to find the new concentrations of ammonia and NH4. Then we're going to react it with sodium hydroxide, let the buffer do what it's supposed to do, take those new concentrations and put them into the final expression. So we do this out. We get, we're going to change, since we're mixing them, we have to change to moles. And there are lots of ways of approaching these types of problems. So if you have a way to do this problem differently, like any of these other ones, and you're sure that it works, then use it. That's fine. I'll be able to follow it on my exam. But if you're in doubt, you're not sure exactly, if it works, or you just want to show me what you've come up with, that's fine. And I'll verify that it's a way of doing it. But yeah, there's tons of ways of doing these problems. And I have to kind of restrain myself. I want to tell you the different ones that different ways of approaching this that I've done in the past, and I've seen other students do. But I don't want to confuse the issue. So I'm just going to go straight out the same way each time. Now, these are the concentrations of ammonia and ammonium ion now that they've been mixed together. The concentration of ammonia before it was mixed was 1.7, now it's 1.02, so it's dropped. This one turned out to be 1 molar, that was just by chance. So we can put these values into this expression to determine the pH of the buffer before we add the base. And so ICE, this is 1.02. And here, since this isn't part of the question that's being asked, and because we've done this in a previous problem, I'm just going to say that X turns out to be 1.84, I should say a previous lecture, and pH is 9.26. This is just because I want to show how that the pH should have gone up, but not that much. But because a buffer does prevent pH from changing, it's not magic. It can't keep it from going up when we add a strong base, but it shouldn't go up that much. Now we have, again, we're going to take 95 mils of our new buffer that we've made and mix it with 5 mils of 0.1 molar. I don't have a molar there above. I forgot to put that in there. There's, and so if they mix, then we have to change to moles. And I don't have to give you 95 mils and 5 mils. It would make your life a little bit easier in the calculations, but it can be anything. I can give you any volumes. You just make sure that you're using the correct volumes. But I gave you 85 and then 3 mils for the buffer and 3 mils for the base. you do it the same way, just a little bit extra work. And the sodium hydroxide, I'm just going to make it OH minus because the sodium hydroxide breaks up into sodium ion and hydroxide ion. And the sodium ion does nothing. It's a spectator ion, so I want to leave that off. And we have, oops, 3 of these. So we have everything now. This is OH minus. Now the OH minus is not going to react with the ammonia because even though it's not neutral, ammonia produces OH minus, so there's no way it's going to react with it. So OH minus is most likely to react with the conjugate acid of ammonia. And the reaction that occurs is OH minus plus ammonium ion goes to water and ammonia. And that's 100%. When you have a strong acid or strong base, they always react 100% until they're done or they've reacted everything away. They've reacted the other, in this case, the weak acid. So, or the conjugate acid. So it's one of the strong base keeps going until it uses itself up or uses up what it's reacting against. I'm going to leave off I guess I'll put them in here. I'm going to say they kind of clutter things up to have all of those zeros in there, even though we want 3 significant figures. This changes to 0.0, sure I'm on the 945 molar. See this OH minus gets completely used up. It should, and there should be some of each of the species for the buffer left behind. Otherwise, the buffer has been used up, and that does happen. I mean, we're not going to do it on a problem like this because we want the buffer to remain intact. But we can, and I should say these are moles, not molars. And then the concentration of, so we left it in moles. We have to divide by our new volume. So this becomes 0.945 molar NH4 plus, and this becomes 0.974 molar ammonia. We have our concentrations back. We have to put them into our new expression. We have our KB expression. So put our new values in, and we're back to our original type of problem. So this is, yep. This would be our KB expression, ICE. Our new concentration for ammonia after the addition of the base is this. Ammonium ion is this. 0 minus X plus X plus X. And because we're coming up on the end here of the 20 minutes, I don't want to overdo it. This becomes, the KB in this case is 1.80 times 10 to the minus 5. And X, the concentration of OH minus is 1.86 times 10 to the minus 5 molar. And that gives us a pH of 9.27. Our pH was 9.26. So it went up very, very slightly, which it should.